A good correlation is usually a dimensionless in correlations. It has a lot of advantages in terms of unit that we use. So normally for mass transfer coefficient the nomenclature is this thing is in form of Sherwood number. NSH equals so in this correlation, for example, we have NSH equals some number, some alpha, so 4 point, some coefficient is here. Into some term, some other term which is so alpha is a coefficient that is experimentally obtained. NRE, NSH is called as the Sherwood number. It is defined as a mass transfer coefficient multiplied by some dimensional parameter, so it is usually L or D or whatever. So in this case it could be L divided by the diffusion coefficient. I am not putting numbers there. So this Ka can be 1 or 2. So depending on what goes here, if it is 1 here, this will also be 1. If it is 2 here, it will also be 2. These two are in the same phase. You can't write Ka1 and Da2 because they are related. So Ka depends on the Da. So wherever you are doing this, the Reynolds number, which is the other. So basically the Sherwood number is the ratio of the convective mass transport to the diffusion mass transport. So it gives you the ratio of that, the magnitudes of that. Reynolds number here again is defined as V L rho by mu. So here again depending on this it could be V1 rho 1 mu 1 or V2 rho 2 mu 2. This is the medium. So this is inertial force. Inertial force is inertia, as we know, is function of the velocity, the inertia, and there is the density there which is mass by volume. Okay. So inertial force divided by the viscous forces on this. So the denominator is viscosity. So the Reynolds number essentially is the velocity is high, Reynolds number is usually high. So that is the only thing that is changing dynamically in the system. So you can have something at higher Reynolds number. And then there is the third quantity called as Schmidt number, which is mu by rho d A. So it is either mu A1, rho A1, dA1 or mu 2 by rho 2 dA2. So the Schmidt number is this divided by this. So mu 1 by rho 1 is called as the kinematic viscosity. There are terms for that, it is given as nu. This does not matter, this changes from textbook to textbook. So this gives you some idea. So if this exists in the correlation, this has this factor dA2. So dA2 will account for now the particular compound that is there, it is now scaled to that particular compound. There is also dA2 in the Sherwood number, so this will also add to that scaling of the particular compound. So a good correlation takes into account everything, all factors are all there, which means somebody has taken the pains to do the experiment for a wide set of compounds, diffusion coefficients, and then for a wide set of velocities and geometry. But this is still geometry, means what we are saying is this L here, the length scale, some length scale. So in this case this L is the same L that is there in your Reynolds number. So we are talking about if we are talking about a river, the interface of a river, we are talking about the length of the water on which there is contact, the fluid is in contact with this length. If your Reynolds number is defined as this length parameter, the Sherwood number also has that same thing there. Sometimes if there is mass transfer on a surface of a particle, the Reynolds number is defined as the diameter of in terms of the diameter of the particle, and then the mass transfer for on the surface of this particle is now defined with the same diameter. So, wherever you will see some correlation sometimes where we want to look at mass transfer between a solid suspended solid particle and water. In those conditions the Reynolds number will be different, therefore the Sherwood number also will be different. So, you have to watch out for the definitions. You cannot use length scale of one this thing and in Reynolds number and Sherwood number it will not match, it will be incorrect. So, you have to be careful about that. So, in this correlation we have now different things. So, they have given us some things. So, there is the parameter called f, which is f is defined as u by gh, and then ux is u star is defined as a term called u star is defined as ghs, and ghs is given by h is the mean stream depth, dA2 is the diffusion coefficient, u is mean stream velocity and so on. So, they have defined everything and you have to follow that quite simply. So, there is another coefficient, people have measured mass transfer coefficients under quiescent conditions for lakes. Now, when you have quiescent conditions for lakes, which means there is a rho A Ka rho A1. So, here this term does not have any it is not clear if this V is not given here, if it is gamma or it is nu or V is velocity or it is velocity only, yeah, it can't be velocity, no? This is no, this is kinematic viscosity, sorry, yeah. So, here there is no velocity term, the only since we have said quiescent conditions, the only convection that is now is because of temperature, there is temperature difference. So, you see that Ti and T1, there is a temperature gradient that exists in the system. So, Ti and are the temperatures at the interface, and the air water interface where T2 is greater than Ti is greater than T1, there is a gradient, and this is the one which is causing so, the water is at a higher temperature than the interface and the air is at a higher temperature at this thing. So, therefore, there may be some differences based on that. Yeah, so density difference is there, the gradient is in this direction and that causes movement. And so, for water side and air side there is given this correlation in terms of the coefficient of expansion and all that. Coefficient of water side mass transfer coefficient at air C interface. C is a huge, C is different, C is not like a lake, okay. So, very difficult to do experiments in C, and one C measurement may not be the same as a different C measurement, but if there is a reason for you to use a C correlation, there are correlations that are there. So, there is a handbook of mass transport, environmental mass transport, in which there are different sections where these correlations are given. People have measured these correlations, and whatever correlation is there, you have to find out what is the how has this experiment been done, so that you can see if it fits your requirement, okay. And this is for mass transfer coefficient, water side mass transfer coefficient, which is Ka21. Stream river bottom mass transfer coefficients, experimental measurement of the rate of solution. So, here is again mass transfer coefficient at the bottom of the lake. So, this is a sediment, this is the coefficient we are talking about at the beginning of this class. So, you look at Ka24, which means that it is in contact with whatever is there on the sediment bed, but it is in water, you have to look at that, and then there is velocity and so, you have to be careful. I mean, this V2 is velocity here, there it is nu, so it is a different thing, viscosity, velocity, you have to make sure the signs are all correct. And there are other correlations that are developed for similar kind of systems. Then we have wind induced water coefficients for unstratified water bodies, which means there are no temperature gradients, but it is wind induced turbulence. So, this is for, if you notice, it is Ka23, which interface is this? it's a sediment water interface. So this is only applicable where it is wind induced sediment water interface, because there is no flow, unstratified water bodies, which is you will see that there is one parameter that is there in this is the velocity of air. The velocity of air is causing enough churning that it is taking it is causing this is air, this is water, this is sediment. This wind is strong enough to cause large scale circulations, that it is affecting a Ka23 at this interface. It is causing a turbulence there, and that is the correlation. So, it is a correlation. So, you can write whatever you want, however you want, you can develop this correlation. It has to be based in some physical observations of that system. And we have natural convection, which is again a density difference, density driven thing. Okay. So, this density difference is defined as this bottom here. And we have evaporation of volatile chemical spill, so which means it is Ka13. Ka13 will be with the air and some solid interface, air and land or air and soil, something like that, or the air side. And so, you see again that correlation has Schmidt number, it has Reynolds number, it has diffusion coefficient. So, it is essentially one of those good, it is like a Schmidt number which is all rearranged here. But they have conditions in the range of Reynolds number is between 1500 and 300,000, and definition of Reynolds number is there, and so on. So, in addition to this, there are a large number of theories for mass transfer. One of them is called as the boundary layer theory for flat plate, for turbulent and laminar flow. So, laminar flow, this is the laminar flow boundary layer theory, which is Sherwood number is 0.664, Reynolds number into this, for Reynolds number less than 5, 10 raised to 5. So, this is a very useful correlation. This is very well tested. It is derived from first principles, which means this is from the Navier-Stokes equation you can derive this for flat plate, and I have written this here. Any reasonably flat surface can be assumed to be this. Now, it is your discretion. So, reasonably flat plate means the plate is rigid, the surface is rigid. So, I can use this for air, land, air, water. I have to be a little careful because water is not exactly rigid, water moves, but if I have nothing else to go for water, I can use this. So, you have to take it with a bit of this thing. So, in all these correlations, there is the length scale for rivers and lakes and all that. This length scale is known as fetch. If it is the length along a river, for example, these correlations is in this case the Sherwood number has a length scale. So, the NRE is defined as L into V rho by mu, where L is the characteristic dimension, the length in the direction of flow, air or water flow. So, you can apply this both, you can also apply this to water, but it is more applicable to air across on surfaces of solid or surfaces of water. It is less applicable for water on sediment, because it is a finite layer, it is not flat plate. Flat plate, the basic assumption of a flat plate correlation is that it is flat and the boundary layer is kind of infinitely extending into the atmosphere. There is no, this is a flat plate. But if I have water, my surface, this is fine, this bottom surface is sediment, and this is soil. But if I have water here, I have another surface here. So, there may be a boundary layer here, and then there may also be a boundary layer on this side, which I do not know exactly. This is not the same as this, but it may not extend fully. This boundary layer may be, it is not a free surface, right? It is not going, it is not a free medium, there is a boundary here. So, the correlation may not exactly be the same as flat plate, but if you do not have anything else, you can use this. But fortunately, there are correlations for streams, water side coefficients, so you can use that. The only problem, only place where you do not have enough correlations is the water side coefficients for streams in air water interface. So, there are very few correlations, as you will see, for this Ka21 for streams. So, then you have to use whatever is available, okay, especially like the ones we saw the beginning of this class. It is a bad correlation, but that is the only thing available, you just have to use it, there is nothing else you can do. So, if I give there are a lot of problems, there are a couple of problems that I have put in a tutorial. So, you can have any kind of scenario. So, I will say there is a barge of vessel. So, you can have lots of problems, scenarios, case studies in this. Okay. There is a barge of vessel carrying heavy loads on water, 1000 tons of a mixture of hydrocarbons. 500 tons of this oil is a dense napple, yeah, and the rest is a light napple, and it spills. Okay. What will happen? So, this problem is very easily formed. There is a barge, there is sediment, and what is the system I am talking about here? It is a river. So, it is a river, it is flowing and it spills. It says 500 tons D napple and 500 tons L napple, light and dense and light, which means when it spills out, one portion of it is going to sit here. There is one large portion that is going to sit on the surface of water, and there is another large portion that is going to go down and sit on the bottom of the river. So, this is the D napple, this is the L napple. Now, in this problem, what will be your risk assessment? What will be the risk assessment here? Several things. One, there is processes that are happening are evaporation, this is dissolution, this is dissolution. Here also something is happening. What is happening here? This is also spreading into the sediment, and this is a process we will discuss now after finishing this set of examples. This is also spreading here inside. We will call it as spreading for the time being. The contamination is spreading downward, so it is going below. So, all these processes are there. So, you have several interfaces at play here. One, this one is Ka14, this is Ka24, this is Ka23, this is something else. There is no convection on this side, it is diffusion based process. So, this is mostly diffusion inside the sediment. There is no mixing here, there is no convective force at all. So, it has to be diffusion based. Yeah. So, there is a velocity of the water, there is velocity of air, all these things come into play. Okay. So, I can make this problem as complicated as I want in terms of what I am looking for. So, I can quickly calculate what is the steady state things I can calculate. I can calculate Na1 4, I can calculate Na2 4, I can calculate Na2 3. These are the 3 steady state fluxes I can calculate with. What we mean by steady state fluxes, I am assuming that the concentrations are all fairly constant during that period of calculation. If I know that they are changing, then I cannot use steady state calculation, I have to use an unsteady state balance. That will change depending on what is the system I am taking and the time period and initial conditions and all that. So, you have to go back to the mass balance and redo your problem. So, for the purposes of this class, we will not go there, at least unless we have some more time. We will just look at this as the main thing. So, this is very common. This is an oil spill on a surface. This is a oil spill contamination of sediments. What we call as oil spill is, oil is a very generic term, oil can be anything. It is a mixture of hydrocarbons, paraffins, naphthalene, everything, all kinds of petrochemicals, anything, it is a chemical spill for all this thing. but a lot of material that is transported on water is usually oil. So, that is why generic term given for oil spills. And this also again undergoes other processes. So, as we looked at, the oil spill on the surface, for example, this one can undergo spreading, it can undergo breakage, dispersion. It can undergo dispersion means it's one large spill may become several small spills and then it will carry forward. And so, in the sediment side here, the oil spill can manifest itself as several these things. So, it can appear depending on the bed, the sediment, if it is smooth, oil will just sit on the surface of it like this, right. But very often the oil spill is not very smooth, it is it's in the form of some waves you can see. So, in this case, if you have these kind of waves, what will happen is, so if I exaggerate these waves and this thing is, it will fill up, it can fill up the oil can, the chemical can fill up the place here. So, this looks like a flat surface, but as dissolution occurs, this and depending on the amount of this thing, the oil can also, the chemical can also occupy something like this. So, people have developed correlations for this. So, one of the correlations that you see here in terms of the water side this things is this one. So, this correlation here Ka24, there is a term here which says delta minus HW. So, delta is a wave height, if this is accounts for the wave, there is no wave. So, the wave height is delta minus HW is the chemical depth in the wave trough. So, wave height. So, what it says is this is delta and this is HW. So, the delta minus HW is a factor in your in the thing. So, if delta equals HW, this will become 0, which means that then this entire thing will go away, only Ka2 by 0.114 V star by SA2 stands. But if there is a, if this is smaller, which means that the delta is bigger than HW, which means there is a small pool of liquid here, then it will influence the mass transfer coefficient there, because the mass transfer coefficient now it has to come through, the liquid has to come through, the structure of the liquid is not the same anymore, the flow will change because it has to go through the wavy this thing, okay, and so on. So, there are examples of how people try to calculate the mass transfer coefficient through correlations and apply it. So, my suggestion to you is to quickly like the dispersion thing, this will be there, we will go through this again later when we finish up the complete discussion of this. But you can start looking at some of the cases here. Yeah. So, very quickly identify many problems that you can have in environmental listing and see which is the mass transfer, appropriate mass transfer correlation in terms of nomenclature that you would use, and if there are any special conditions along that. So, in this case the second problem again is bottom spill. Yeah. So, tomorrow we will discuss the sediment part of the spreading, and more importantly after the spreading is done, the release again, re-release into the water, which is what we will talk about. This constitutes as historically contaminated sediment, which means it takes several decades for that to happen, and because the process is based on diffusion. So, this will give you a very good idea of what we call as fate and transport, because fate and transport occurs over a long time, and it's not a quick thing that happens, and the reason why people are interested in it is because it goes on for several decades and whether we can assess the risk. Okay.